Chapter 7. Managing Growing Projects with Packages, Crates, and Modules. As you write large programs, organizing your code is important because it'll become impossible to keep track of your entire program in your head. By grouping related functionality and separating code with distinct features, you will clarify where to find code that implements a particular feature and where to go to change how a feature works. The programs we've written so far have been in one module in one file. As a project grows, you can organize code by splitting it into multiple modules and then multiple files. A package can contain multiple binary crates and optionally one library crate. As a package grows, you can extract parts into separate crates that become external dependencies. This chapter covers all these techniques. For very large projects of a set of interrelated packages that evolve together, Cargo provides workspaces, which we will cover in the section Cargo Workspaces in Chapter 14. In addition to grouping functionality, encapsulating implementation details lets you reuse code at a higher level. Once you've implemented an operation, other code can call that code via the code's public interface without knowing how the implementation works. The way you write code defines which parts are public for other code to use, and which parts are private implementation details that you reserve the right to change. This is another way to limit the amount of detail you have to keep in your head. A related aspect to organization and encapsulation is scope. The nested context in which code is written has a set of names that are defined as in scope. When reading, writing, and compiling code, programmers and compilers need to know whether a particular name at a particular spot refers to a variable, function, struct, enum, module, constant, or other item, and what that item means. You can create scopes and change which names are in or out of scope. You can't have two items with the same name in the same scope, and tools are available to resolve name conflicts. Rust has a number of features that allow you to manage your code's organization, including which details are exposed and which details are private, and what names are in each scope in your programs. These features are sometimes collectively referred to as the module system and include packages, a cargo feature that lets you build, test, and share crates, a tree of modules that produces a library or executable, modules and use let you control the organization, scope, and privacy of paths. Paths, a way of naming an item such as a struct, function, or module. In this chapter, we'll cover all these features, discuss how they interact, and explain how to use them to manage scope. By the end, you should have a solid understanding of the module system and be able to work with scopes like a pro. Packages and crates. The first parts of the module system we'll cover are packages and crates. A crate is a binary or library. The crate root is a source file that the Rust compiler starts from and makes up the root module of your crate. We'll explain modules in depth in the section Defining Modules to Control Scope and Privacy. A package is one or more crates that provide a set of functionality. A package contains a cargo.toml file that describes how to build those crates. Several rules determine what a package can contain. A package must contain 0 or 1 library crates and no more. It can contain as many binary crates as you'd like, but it must contain at least one crate, either library or binary. Let's walk through what happens when we create a package. First, we enter the command cargo new. We will call it P and C. When we entered the command, cargo created a cargo.toml file. Yeah. Giving us a package. Looking at contents of cargo.toml, there is no mention. Where am I? Well, let me bat it real quick. There's no mention of source/main.rs because, oh hey, look, there's my email address. Well, you know, be friendly. Likewise, where am I? No mention of a source/main.rs because cargo follows a convention that source/main.rs is the crate root of a binary crate with the same name as the package. Likewise, cargo knows that if the package directory contains source/librs, the package contains a library crate with the same name as the package, and source/librs is its crate root. Cargo passes the crate root files to rustc to build the library or binary. Here we have a package that only contains source/main.rs, meaning it only contains a binary crate named my project. If a package contains main and lib, it has two crates, a library and a binary, both with the same name as the package. A package can have multiple binary crates by placing files in the source/bin directory. Each file will be a separate binary crate. A crate will group related functionality together in a scope so the functionality is easy to share between multiple projects. For example, the rand crate we used in Chapter 2 provides functionality that generates random numbers. We can use that functionality in our own projects by bringing the rand crate into our project scope. All the functionality provided by the rand crate is accessible through the crate's name, rand. Keeping a crate's functionality in its own scope clarifies whether particular functionality is defined in our crate or the rand crate and prevents potential conflicts. For example, the rand crate provides a trait named RNG. We can also define a struct named RNG in our own crate. Because a crate's functionality is namespaced in its scope, when we add rand as a dependency, the compiler is not confused about what the name RNG refers to. In our crate, it refers to the struct RNG that we defined. We would access the RNG trait from the rand crate as rand::RNG. Let's move on and talk about the module system. Defining modules to control scope and privacy. In this section, we'll talk about modules and other parts of the module system, namely paths that allow you to name items, the use keyword that brings paths into scope, and the pub keyword to make items public. We'll also discuss using the as keyword, external passages, and the glob operator. For now, let's focus on modules. Modules let us organize code within a crate into groups for readability and easy reuse. Modules also control the privacy of items, which is whether an item can be used by outside code, public, or whether it's an internal implementation detail and not available for outside use. Private. As an example, let's write a library crate that provides the functionality of a restaurant. We'll define the signatures of functions but leave their bodies empty to concentrate on the organization of the code rather than actually implementing a restaurant in code. In the restaurant industry, parts of a restaurant are referred to as front of house and others as back of house. Front of house is where customers are and includes hosts, seating customers, servers taking orders and payment, and bartenders making drinks. Back of house includes the chefs and cooks in the kitchen, dishwashers cleaning up, and managers doing administrative work. To structure our crate in the same way that a real restaurant works, we can organize the functions into nested modules. Create a new library named restaurant by running cargo new lib restaurant, then put the code in listing 7.1 into source libars to define some modules and function signatures. So we will cargo new VCS none lib restaurant. Good job. And we've got a source, including librs. Great. Open up my librs. I've got a handy test. We say mod front of house. Mod hosting. Function add to waitlist. And function seat at table. Okay, so inside mod front of house, but outside of mod hosting, we have mod serving. Well, that makes sense. We will have function take order, function serve order, function take payment. All right. Q. Recording at. Are we recording? You can do macros, right? Q. Recording at something there? I really don't. Oh. Oh no. Alright, let me figure out how to do macros. I'll be right back. And then go to the end of it. And stop recording. Okay. So now at W Yahoo, and then at Groovy. Am I recording? Yes, I am. We define a module by starting with the mod keyword and then specify the name of the module, in this case, front of house. We place curly brackets around the body of the module. That's all that. Inside modules, we can have other modules, as in this case with the modules hosting and serving. Modules can also hold definitions for other items, such as structs, enums, constants, traits, or, as in listing 7.1, functions. By using modules, we can group related definitions together and name why they're related. Programmers using this code would have an easier time finding the definitions they want to use because they could navigate the code based on the groups rather than having to read through all the definitions. Programmers adding new functionality to this code would know where to place the code to keep the program organized. Earlier we mentioned that main and lib are called crate roots. The reason for their name is that the contents of either of these two files form a module named crate at the root of the crate's module structure, known as the module tree. This tree shows how some of the modules nest inside one another, such as hosting nests inside front of house. The tree also shows how some modules are siblings to each other, meaning they're defined in the same module. Hosting and serving are defined within front of house, so they're siblings. To continue the family metaphor, if module A is contained inside module B, we say that module A is the child of module B, and that module B is the parent of module A. Notice that the entire module tree is rooted under the implicit module named crate. The module tree might remind you of the file system's directory tree on your computer, and we did it on purpose. Just like directories in a file system, you use modules to organize your code. And just like files in a directory, we need a way to find our modules. Paths for referring to an item in the module tree. To show Rust where to find an item in a module tree, we can use a path in the same way we use a path when navigating a file system. If we want to call a function, we need to know its path. A path can take two forms: an absolute path, which starts from crate root by using a crate name or a literal crate, and a relative path, which starts from the current module and uses self, super, or an identifier in the current module. Both absolute and relative paths are followed by one or more identifiers separated by double colons. Let's return to the example in listing 7.1. How do we call the add to waitlist function? This is the same as asking, what's the path of the add to waitlist function? In listing 7.3, we simplified our code a bit by removing some of the modules and functions. We'll show two ways to call the add to waitlist function from a new function, eat at restaurant, defined in the crate root. Note that this example won't compile just yet. We'll explain why in a bit. Let us see. I will say, oops. Oh, okay, so hash bang allow. I wonder if I can say dead code, comma, space, unused variables. Oh my. It seems to work. I guess. I mean, I don't know if I have any variables yet, but I surely it would it would object if that didn't work. Okay, so in the mod front to house, you have hosting and a function add to waitlist. Now we are going to have a public function eat at restaurant. Pub fun eat at restaurant. We got an absolute path here. It's going to be create colons front of house colons hosting colons add to waitlist. And then, of course, a relative path. So we start right here at front of house. Is that because that's where we are? Don't know. Front of house, colons, mosting, hasting, hosting, colons, add to waitlist. The first time we call the add to waitlist function in eat at restaurant, we use an absolute path. The add to waitlist function is defined in the same crate as eat at restaurant, which means we can use the crate keyword to start an absolute path. Okay, it says the add to waitlist function, blam, is defined in the same crate as eat at restaurant, blam, which means we can use the crate keyword to start an absolute path. Well, sure, because the crate keyword refers to our root crate, I guess, or project. Yeah, this is essentially the bottom of our unique code. If we have other crates that we've added, that we have imported, then we could name them here instead. After crate, we include each of the successive modules until we make our way to add to waitlist. You can imagine a file system with the same structure, and we would specify the path /front of house /hosting /add to waitlist to run the add to waitlist program. Using the crate name to start from the crate root is like using / to start at the file system root in your shell. The second time we call add to waitlist in eat at restaurant, we use a relative path. The path starts with front of house, the name of the module defined at the same level of the module tree as eat at restaurant. Okay, so in our module tree then, front of house and hosting, and eat at restaurant will be in the same, will be siblings in the module tree. Right, because the alternative would be that we're saying eat at restaurant is in the module hosting, or is in the module serving. It is not at all clear why that should be. Oh, well, no, because if we put, right, if that's not true, the other alternative would be that if this public function was in the module front of house, then it would be a child of front of house, but as it is a sibling of front of house. And I suppose that makes sense because here in libars, we are declaring the module front of house, and then after this is all closed up, declaring this public function. Right? Okay. The path starts with the front of house, the name of the module defined at the same level of the module tree as eat at restaurant. Here the file system equivalent would be using the path front of house /hosting /add to waitlist. Starting with a name means that the path is relative. Interesting. Choosing whether to use a relative or absolute path is a decision you'll make based on your project. The decision should depend on whether you're more likely to move item definition code separately from or together with the code that uses the item. For example, if we moved the front of house module and the eat at restaurant function into a module named customer experience, we would need to update the absolute path to add to waitlist. But the relative path would still be valid. However, wait a minute, let me think about that. Okay, so it says if we want to take front of house and eat at restaurant and move them into a separate module called customer experience, then this relative path would still work. It would be just fine because we're starting at front of house, which is together here at the same level in the tree. But on the other hand, if I need to read the next part. However, if we moved the eat at restaurant function separately into a module named dining, the absolute path to the add to waitlist call would stay the same. So if we move this out and it's no longer here next to mod, so it's no longer the relative. Okay, let me read this. But the relative path would need to be updated. Right, so the absolute path would be fine because we need to get to this add to waitlist function, which is in hosting, which is in front of house, which is in crate. The relative path would need to be adjusted or just not used because here we need the add to waitlist function, which is in hosting, which is in front of house, but where's front of house? Our public function wouldn't know where eat a restaurant wouldn't know where front of house is because eat a restaurant would be in some other module where it's not adjacent to front of house in a tree. Maybe it's a cousin, but it's not a sibling. The absolute path to the add to waitlist call would stay the same, but the relative path would need to be updated. We tend to specify absolute paths because it's more likely to move code definitions. Ugh, I don't like that. We tend to specify absolute paths because we are more likely to move code definitions and item calls independently of each other. We tend to specify absolute paths, so it's this one, because it's more likely that we will want to move code definitions away from item calls, or item calls away from code definitions. Okay? So prefer absolute paths, it says. Let's try to compile this and find out why it won't compile. Can do. Am I recording? Yes, I am. Cargo build, it says. Why can't we cargo run? Okay, so there's no binary. So let's cargo build. That's what it told us to do. Okay, cargo build. Cargo build, and we've got some output. So module hosting is private. Module hosting is private. Well, I think I know where this is going. Hosting shall be a public module. Oh, should I look at that? What's the deal there? Function add to waitlist is private. Oh, I'm getting ahead. I guess I still have to read it out loud, but I have a feeling this is what they're about to tell me. We need to put the pub keyword in front of these things so that they can be used by a different module. Public function is in a different module than hosting is. Because public function is in the crate module, I think. So we will cargo build. And here we are. We've gone and done it. Right. The error messages say that the module hosting is private. In other words, we have the correct paths for the hosting module and the add to waitlist function, but Rust won't let us use them because it doesn't have access to the private sections. Modules aren't only useful for organizing your code, they also define Rust's privacy boundary, the line that encapsulates the implementation details external code isn't allowed to know about, call, or rely on. So, if you want to make an item like a function or a struct private, you put it in a module. The way privacy works in Rust is that all items, functions, methods, structs, enums, modules, constants are private by default. Items in a parent module can't use the private items inside child modules, but items in child modules can use the items in their ancestor modules. Isn't that just like life? The reason is that child modules wrap and hide their implementation details, you better believe that, but the child modules can see the context in which they're defined. To continue with the restaurant metaphor, think of the privacy rules like the back office of a restaurant. What goes on in there is private to the restaurant customers. So not the wording I would have chosen. What goes on in there is not revealed to, is not available. It is private. It is privately, well, okay, I understand what it means, but private to restaurant customers doesn't sound right. Okay, I feel like private to office managers would make sense. Moving along. But office managers can see and do everything in the restaurant in which they operate. Okay, sure. So what they just said is if we want to have... Right, okay, so with a back of house module, as long as we don't give it the private flag, the public flag, and it's, let's say it's defined here in librs. It has access to everything in the whole restaurant outside of other modules that aren't public. But just walking in the door of the restaurant does not give you access to the back of restaurant module. Rust chose to have the module system function this way so that hiding inner implementation details is the default. That way, you know which parts of the inner code you can change without breaking outer code. But you can expose inner parts of child modules to code, child modules code. Oh, snap. There should be an apostrophe there. You can, right? You can expose that because this is possessive. Should be an apostrophe after the S. Wonder if they fixed this. But you can expose inner parts of child modules code to outer ancestor modules by making an item public using the pub keyword. Exposing paths with the pub keyword. Let's return to the error we had in listing 7.4 that told us hosting is private. We want the eat at restaurant function in the parent module to have access to the add to waitlist function in the child module, So we mark the hosting module with the pub keyword. Yes, pub mod hosting. Unfortunately, the code in listing 7.5 still gives us an error. Uh-oh, create front of house hosting add to waitlist is still private. What happened? Adding the pub keyword in front of mod hosting makes the module public. With this change, if we can access front of house, we can access hosting. Well, that seems... Aha! Great. So if we can access front of house, we can access hosting. So is there any relevant, like if I put pub mod front of house, does that mean that, I suppose there's some implementation for that. Right. Okay. But the contents of host, so we can access hosting. Sure. Hosting. But the contents of hosting are still private. Making the module public doesn't make its contents public. The pub keyword on a module only lets code in its ancestor modules refer to it. Okay. If add to waitlist is still private, well, the privacy rules apply to structs, enums, functions, and methods as well as modules. Let's also make the add to waitlist function public by adding the pub keyword before its definition. We now have mod front of house, pub mod hosting, pub function add to waitlist. And then pub function eat a restaurant, create front of house hosting add to waitlist, absolute path front of house hosting add to waitlist. Now the code will compile. Let's look at the absolute and the relative path and double check why adding the pub keyword lets us use these paths in add to waitlist with respect to the privacy rules. In the absolute path, we start with crate, the root of our crate's module tree. Then the front of house module is defined in the crate root. The front of house module isn't public, but because the eat at restaurant function is defined in the same module as front of house, that is, eat at restaurant and front of house are siblings, we can refer to front of house from eat at restaurant. Next is the hosting module, marked with pub. We can access the parent module of hosting, so we can access hosting. It's marked with pub. And that is why getting here lets us access this. Finally, the add to waitlist function is marked with pub, and we can access its parent module. So this function call works. In the relative path, the logic is the same as the absolute path, except for the first step. Rather than starting from the crate root, the path starts from front of house. The front of house module is defined within the same module as eat at restaurant, so the relative path starting from the module in which eat at restaurant is defined works. Then, because hosting and add to waitlist are both marked with pub, the rest of the path works and this function call is valid. Starting relative paths with super. We can also construct relative paths that begin in the parent module by using super at the start of the path. This is like starting a file system path with the ... syntax. If you are watching this video and you don't understand these references, it appears that they are talking about Unix-like operating systems. So let's go to desktop. So here I am in desktop. Right, that's where I am. And so if I want to go from desktop to, let's say, videos, right, or projects. We'll go to projects. Then I can say change directory. Now I can't go straight to projects from here because I am in desktop. If I try, it'll tell me, sorry, I don't know what you're talking about. Instead, I can say change directory to / projects. So the .. is the same as saying change directory to, well, I guess it's not quite the same, but because if you look at the absolute path of where I am is home Altman desktop. Well, so this is interesting. I mean, I just learned something about Rust by talking through this. And there it is, relative paths with super. Right. So, I mean, an absolute path has to be absolute. And the first, oh yeah, just kidding. The first, so I can get into desktop like this. There we are. And then get out. This backs me up. It goes up a level. It goes to the parent. So now I'm no longer in desktop. Right, and if I use .. I think I just did this. So .. is refers to the parent directory. So .. in this case is short for cd .. change directory. I'm using this shell, and that's giving me well, I'll show you. Ooh, yuck. No. Set. No. Term GUI colors. Better. So I have set opt where something in here. Set opt. Oh, here's a whole list of my things, that options I have set. Auto CD. It means if you give it the name of a directory it can get to without saying cd or change directory, it will assume that's what you want to do. Okay. So here I am in home, and right, okay, so a little bit more like shell syntax, I guess. So if I want to get into desktop, I can give it this / prefix, and that it creates a relative path from where I am. Right, the dot, I guess the dot represents the directory I'm actually in. So it's like, okay, so change directory to desktop, but I have that / in front of it, so it's like change directory from right here into /desktop. So let's see. After that, we're going to go into projects, but first we're going into desktop. So now we are on desktop. I can say cd .. right, and that does not refer to desktop, which is where we are. That refers to the parent directory of desktop, which is my home, and that is why I can say PR autocomplete, and it knows what I'm talking about. Now this is all still relative, and this is what sort of clicked for me talking about it here. Is super is yeah, the super keyword is still relative. Ugh. All right. This is like starting a file system path with the .. syntax. Why would we want to do this? Consider the code listing here that models the situation in which a chef has to fix an incorrect order and then personally brings it out to the customer. the function fix incorrect order calls the function serve order by specifying the path to serve order starting with super. Okay. I've got to put this in my code now. Should I go down below this function or... No, okay, so I'm going to try to keep the modules together, right? So we'll have a module. Yeah, here's our back of house module, and we are... So it's... I mean, I guess it's going to be... Yeah, so it's... Okay, it's private by virtue of its being a module. And we're not going to make it public. So let's see what else we do. Fix incorrect order. Alright, and so, yeah, so we have cook order, which is in back of the house. Okay, yes, so we have cook order is called here, right? And I'm glad that it's warning me about that, because we're calling something we haven't defined. Now super serve order, right? There's a problem with that too, because it's calling not found. Well, yeah, let's see if defining cook order solves both of those. Yes, it do. No, it don't. Okay. Well, they'll walk us through it. The fix incorrect order function is in the back of house module. Uh-oh. That was supposed to work. Did I leave something out? Oh, well I didn't make the serve order function. Goof. Google Moogle. This is irritating to me because they are... I wonder if they did this on purpose. If they... In this section of the book where they're explaining how to organize your stuff, they'll give me this. And I mean, I guess I could have just plopped that down right in the middle, but I sort of want my modules in one place and my functions in another place. Alright, okay, so we have a function, serve order. And that should... Yes. That should... fix it. Yes, okay. The fix incorrect order function is in the back of house module. So fix incorrect order is in this module, back of house, which in this case is crate, the root. So the absolute path would be crate, back of house, fix incorrect order, serve order. No. Serve order. Right. No, where's serve order? Serve order. It would be crate. Wait, what? The fix incorrect order. Yeah, because now we're in this module. Yes. Okay. So the absolute path would have to start from. Would it? Yes. Huh? Okay. I've got a way to think of this. Fix incorrect order is in back of house. And fix correct order needs to call serve order. So from fix incorrect order, which is in back of house, the shortest way to get to the serve order function from here, remember we're talking about paths, is to say super, which begins a relative path, begins a relative path from the parent of the module we are in, which in this case is crate. So it's just we're now out of the back of house module, and we don't have to do anything else because there it is, serve order right there. So this super serve order is saying the fix incorrect order is saying, okay, you're going to use serve order. Don't see it, do you? Nope. Well, let me tell you how to get there. First, super. Whoop. Bump. Oh, here I am in the parent module. Look around. Do I see it? Hey, there it is. Right. This case is create the root. From there, we look for serve order and find it. Shazam! We think since we used super, that this is what we're saying. We're saying that we think back of house and serve order are gonna stay together. They're gonna stay in the same relationship, and if we move them because we're reorganizing stuff, they're both going the same place. So that's why we used super, and that way we will have fewer places to update code in the future if this code does get moved to a different module. Right. So super is pretty handy because it starts relative paths from the parent module. So then you can move siblings together and you don't have to change the paths. Whereas relative paths are good as long as you're not gonna take apart. Relative paths in general are good as long as you're going to keep things together. But if you have something such as a function serve order and a module back of house, well, I don't know. They're making a big assumption that I'm going to want back of house and serve order in, organized in the same place. But the point is, this is how you do it. Making structs and enums public. We can also use pub to designate structs and enums as public. But there are a few extra details. If we use pub before a struct definition, we make the struct public, but the struct's fields will be private. We can make each field public or not on a case-by-case basis. So here we define a public back of house : breakfast struct with a public toast field, but a private seasonal fruit field. This models the case in a restaurant where the customer can pick the type of bread that comes with a meal, but the chef decides which fruit accompanies the meal based on what's in season and in stock. The available fruit changes quickly, so customers can't choose the fruit or even see which fruit they will get. We need another. Okay, we've got the back of house module and some. Whoa. They are confusing me on purpose. Okay, so we now have within back of house, we're going to have a pub struct called breakfast with a pub field toast, which is a string, and another field seasonal fruit, which needs to be a string as well. It is not public. And within the module back of house, right below our struct definition, will be an implementation for the breakfast struct. We will implement a public function called summer with parameters toast, which is going to be a reference to a string, or I should say which is going to be a reference to a slice, or is that just a slice? And we are going to return breakfast, an instance of breakfast. So here this is what the breakfast looks like that we're going to return. This is like, spoiler alert, breakfast coming out. So what breakfast? Well, this breakfast. So our breakfast is, do I have to say toast, string from toast? I could have sworn they told me that as long as our parameter is the same as the name of the struct, we don't have to name it here. Let's try this. Toast string from toast. Unt seasonal. Oof. Yeah, seasonal fruit, and this one is not one of our arguments, so we do have to. I mean, I'm seeing them red squiggles. I don't see one under string. No, I do. Oh, golly. String from peaches. Alright. What, breakfast? What do you want, breakfast? What do you need? Missing field toast. Expected, that stuff. We found a string. Well, fine. You know what? Fine. Oh, wow. You know, I didn't really do a whole lot there, did I? What if I don't have the word toast? See, that's what I was trying to do. That doesn't let me do it? Fine. Fine. You win. You win, Clippy. Or RLS or whatever. Okay, so now we got a public function, eat at restaurant. Order breakfast in the summer with rye toast. Change our mind about what bread we'd like. Okay. That gets you on a different list. Alright, so out of that, in the, how do we say, crate scope, we will pub fun eat at. Do we already have that? Yes. We're changing things. So I'll just drop it right on in here. Let mutable meal. It's gonna be back of house. Give me some of that good breakfast during the summer. Don't think we defined that. Did we? Yes, we did. Summer, and we're gonna need it to be rye. And meal dot toast. So we have implemented meal dot toast. Tell me about that. Let's see. Meal dot toast. Oh, that's from the struct. Right. Meal dot toast equals string colons from wheat, and then print line macro Excuse me. I hate to be a bother, but may I please change my toast to wheat? Yikes. Change my toast to variable. Meal.toast. I think I might need some word wrap here. Alright. This line won't compile if we uncomment it. Meal.seasonal fruit. Right. Okay, because that is because in the struct breakfast, toast is a public field, but seasonal fruit is not. You get what you get, and you don't pitch a fit. Okie doke. Because the toast field in back of house colons breakfast is public in Eat It Restaurant, we can write and read to the toast field using dot notation. Notice that we can't use the seasonal fruit field in Eat It Restaurant because seasonal fruit is private. Try it. No thanks. Also, note that because back of house colons breakfast has a private field, the struct needs to provide a public associated function that constructs an instance of breakfast. We've named it summer here. If breakfast didn't have such a function, so we have a public function implemented on the breakfast struct. And if we didn't have that, we couldn't create an instance of breakfast in Eat It Restaurant because we can't set the value of the private seasonal fruit in Eat It Restaurant. Oh, I see. So this public function implemented on breakfast we have to provide a public associated function. Huh. Yeah. So this has to be public, and it has to be an associated function of breakfast. Because we have a non-public field in breakfast, seasonal fruit. So here in Eat It Restaurant, let meal equal back of house colons breakfast colons summer rye. Now we've gotten into the back of the house. We've gotten into breakfast. We're getting summer here. Okay, so public func summer takes toast as an argument, as toast as a parameter. I don't suppose it would work as well, or it might be different if we tried to let it have seasonal fruit as a parameter, because then maybe we couldn't even pass that parameter. Here we can pass rye. Could we pass? I don't know. All right. Okay. So in contrast, if we make an enum public, all of its variants are then public. We only need the pub before the enum keyword. Yeah, because enums and structs are pretty different. So in our module back of house, we will have a new pub enum appetizer, which consists of the soup, the salad, the soup, or the salad, thank you very much, and that is all. So coming back into Eat It Restaurant, we'll say let order 1 equal back of house colons appetizer colons soup, and we will say let order 2 equal all that. Because we made the appetizer enum public, we can use the soup and salad variants in Eat at Restaurant. Enums aren't very useful unless their variants are public. It would be super annoying to have to annotate all enum variants with pub in every case, so the default for enum variants is public. Ooh, wait. Is this 2 not supposed to be there? It would be annoying to have to annotate all enum variants with pub in every case. So, the default for enum variants is to be public. No, it's fine. Structs are often useful without their fields being public. So, struct fields follow the general rule of everything being private by default unless annotated with pub. Right, it might be better to say, instead of saying structs are often useful without their fields being public, they could say structs are often useful if it's often useful to have private fields in structs. So struct fields follow the general rule of everything being private by default unless annotated with pub. Yeah, so this makes me think of mutability or immutability. Everything is immutable by default unless you say it's not immutable. So everything is private by default unless you say that it is public. And then you really got to say it. You got to mean it. You got to go in and say it everywhere you mean it. There's one more situation involving pub that we haven't covered, and that is our last module system feature, the use keyword. We will cover use by itself first, and then we'll show how to combine pub and use.